Hello, everyone. My name is Saad Harishi. I'm a first-year PhD student at the University of Montana, working with Professors Jordan Maloff and Jesse Johnson. Today, I want to share with you our project on predicting wildfire rate of spread using machine learning and remote sensing. As we all know, wildfires are a global cause of concern that has severe human, economical, and environmental impacts. In 2017, the NIST reported that wildfires cost between $71 and $347 billion each year. And due to climate change, many regions are getting hotter and drier, which lengthens wildfire seasons and exacerbates their effects. Fire management, mitigation, and prevention all hinge on our ability to predict the spread of fires accurately. In the case of a wildfire, firefighters are deployed either at or a distance away from the burning edge. Therefore, predicting fire spread is essential to ensure the safety, but also the effectiveness of these interventions. Better wildfire mitigations also allows us to better mitigate climate change impacts through reducing greenhouse gas emissions, preserving our carbon storing forests, avoiding power outages, enhancing grid reliability, and also preventing transportation system failures, all of which help to break the reinforcing feedback loops of climate change on wildfires. One of the quantities that are used to describe fire behavior is rate of spread, or ROS for short, and is defined as the speed with which the fire is moving away from the site of origin. On the right are two superimposed fire perimeters with white arrows showing the evolution of the fire between the two timestamps. A major challenge of fire mitigation is the unpredictable behavior of wildfires. What we see here are two growing perimeters from the 2018 Oregon wildfires. On the left is a plot of the state of Oregon and the fire growing on the bottom left. And on the right, we've zoomed in on those perimeters. Notice the erratic and unpredictable fire growth from one timestamp to the next, which lessens the effectiveness of field interventions. Field managers have been relying on FlamMap and other statistics-based models for decision-making in firefighting. These traditional models take as input the various factors that are known to influence fire spread, then assume a functional form based on physical theory and lab observations under ideal conditions. For example, FlamMap assumes that all environmental conditions, such as wind and fuel moisture, are held constant in time. However, this assumption is incompatible with conditions observed in the real world, which significantly hinders these models' predictions and accuracy. On the other hand, advances in remote sensing have unlocked unprecedented access to data on fire behavior, leading to the potential adoption of generalized and more complex function finders like neural networks, which are better suited to explain the observed behaviors and possibly even discover relationships we didn't previously understand. So to understand how neural networks work at a high level, we can look at the following example. We have on the left our set of inputs, in this case, high wind, a steep topography, and a dense fuel. These data are passed through each layer of neurons, and finally the model produces an output, in this case, of 0 chains per hour. When we compare this output to the ground truth, we realize that it's a bad answer. Given these conditions, one would expect a high ROS. So this feedback is used to update the model weights and improve its future predictions. At the next iteration, the new weights lead to a more realistic prediction, this time of 46 chains per hour. Now, the challenge with neural networks is that they work primarily with data and don't inherently grasp physics concepts. However, we can leverage our current physical models to jumpstart their understanding of physical phenomena. This approach is known as physics-informed neural networks, and it allows these models to make more accurate predictions while respecting physical constraints. This results in improved prediction accuracy and reduces the need for large amounts of training data. So this is what we have done so far. On the right, you can see two fire perimeters over 12 hours. The gray shows the previous perimeter, and the color contour depicts the current one. Dark colors signify short travel, while bright colors indicate longer distances. So we have used these fire perimeters from NASA's open source VIIRS dataset to calculate the distance that these fires have traveled through each 12-hour period, which then gives us the ground truth ROS we're trying to predict. We have also downloaded Landfire.gov, NASA, and USGS data to get the input features we need to train our neural network and match the values based on the fire event. Our next step would be to train our neural network to predict the ROS given the natural conditions. That's all I have today. I hope that this piqued your interest, and if you have any recommendations or feedback, please feel free to get in touch with me, Jordan, or Jesse, and thank you all for your attention.